Ready, start this. Okay. Oh, that's what I wanted to ask you guys. I want to ask, because last time we moved the test. So I just want to confirm that test 2, the date is still going to work. I've got it set for Monday the 20th.
That's soon.
Yeah, I know, that's why I'm asking.
It's a shorter test than that's okay.
I could bump it to the Wednesday, but I do want to have 80 minutes. So
we have a communications midterm on the 23rd, I think.
oh, okay.
So I don't think that's really.
Yeah, I'm taking requests, I guess.
I don't think you can really decide.
Yeah.
I don't know, 20th sounds good.
20th is good?
Yeah.
Okay.
What day is Wednesday?
This Wednesday, the 22nd.
Oh, no, the final.
Oh, the final is on the 15th, Friday the 15th, I think.
Oh, that's just the review. Okay.
Yeah. Oh yeah, that's just the review class. Yeah. 20th is okay? Well, I am and I am not. I'm flexible. Okay, as long as it's good, then we'll keep going with that. All right. A little bit of review. We got to start exponents finally. Exponential functions on Friday. It's just a little blip of a class though. Exponential functions are things like if we have f of x is equal to a times 1 plus r to the power of x, right? It's when the variable is in the power or in the exponent. We said that, okay, well, A is your initial value, right? So whatever the population size was initially or whatever initial investment, right? We talked about compound interest is an exponential function. And so whatever the initial value is, so at f of 0, it's going to be A, right? Which also means that the y-intercept is at A, right? When x is 0, y is A. And so that's the initial value. R is the rate, right? So if R is between, let's see here, R is a rate. Let me just clarify that. R is a rate of growth if R is between 0 and 1, right? It's going to be usually given as a percentage, right? 7% per year or something like that. But we convert that to a decimal, right? Because for math, we have to work with the decimal or the proportion. And so, or decay if, and let me just bump this down more. I've got it up my sleeve. There, if R is between -1 and 0, right? So if you have a negative growth rate, right, then that's going to be decay. So sometimes what we do is we we combine 1 plus r into just one variable b, it's still 1 plus r. Okay. So, or we can write f of x is a times b to the power of x, where b is 1 plus r. So then, okay, if we have growth, then 1 plus r is going to be a value greater than 1, right? 1.07, that's a 7% growth rate, right? And so if r is between 0 and 1, right, then we have growth, which means that b is going to be greater than 1, greater than or equal to 1. Yeah. Now on the flip side, if the rate is negative, I guess it can't include 0 on both of these. Fine. I'll cut it from one of the sides. It doesn't matter. If it's a rate of change of 0, then nothing's happening. So if I have a negative rate, right, then we know that that's decay. But what happens in terms of our b, right, is 1 plus negative 0.07, for example, right? And so now this is going to be less than 1. Okay, and so if r is between -1 and 0, then we have decay, and b is going to be less than 1. We're going to force it to be greater than 0 because otherwise it kind of makes a mess, right? We force this. And so what we're going to have is we're going to have some base b, which is either going to be some decimal value, right? So some small value less than 1, but greater than 0. Or if it's greater than 1, then we have growth. And so for us, what's going to happen is if we have a b between 0 and 1, then in general, this distribution, or this sorry, not distribution, this function, the graph is going to look like this, right? That's decay. Okay? Whereas if we have growth, then it's going to look something like this. Right? So just looking at b or 1 plus r, it doesn't matter because they're the same, is going to tell you the general direction of the graph. Okay? And I posted the assignment a little bit prematurely because we didn't have a chance to finish the section, but you already have the tools, so you could have picked through it and you can do it. I know you can, but we're going to do some examples of things like if you know that this exponential function goes through these points, then what's the graph, or not what's blah, 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 graphs, barf. Then what's the function, right? That kind of thing. But before we do, I'll call that kind of the end of the review. I had kind of a, while I have mini panicky moments often, but I thought, we never talked about the exponent rules or exponent laws. So it is something that I've assumed that you kind of have up your sleeve. No, I have been assuming it, but that's rude of me. And so I think this is a good, yeah, sorry about that. But just like order of operations, BEDMAS, which is order of operations, just like just general math things, these are just rules that you are now expected to memorize and have and just know and apply and just have them, okay? And so let's talk about each of these. we can start off nice and slow. And I stole this from a different textbook because I couldn't find anything like this in our textbook. So do you want me in the picture or out of the picture? Yeah, so it'll be in our notes, obviously. But if you want to snap a picture, that's good. Okay, so we'll start off nice and slow. We're going to let a be greater than 0, which just means that because negative bases kind of behave strangely, just like we touched on here. Okay, so we're going to force the base, which is the base of the exponent, to be positive. And then m and n are in the set of real numbers, which just is saying it can be they can be any numbers, right? And so here, this is really just saying m and n can be any number. The set of real numbers, remember, is the set of values from negative infinity to positive infinity and every increment in between, which is an infinite number between even 1 and 2. You can break it down and make it super small. So it's a little bit mind-boggling. So any number will do. First rule of exponents is that if you have a times a times a n times, then you can rewrite it as a to the power of n. That's fair, I think. And so here, let me just clarify that there are n is here being multiplied together. Right? One of the things that, so we're usually pretty conditioned to only read these rules from left to right, but in our case, a lot of the time we're going to be moving from right to left, so we need to be really flexible on how we move between these two sides. So, for example, if I have a to the power of m times a to the power of n, then one of the key things to notice here is that you have to have the same base. Okay. So I'll call this a is the base. So here you have to have the same base. And if you do, you can rewrite it as a to the power of m plus n. Okay. So if you're multiplying the same bases, then you end up at a to the power of m plus n. Or often what we do is we want to move from this setup where I can break it up into a to the power of m plus n. Then I can rewrite it as a to the power of m times a to the power of n. Okay. So being able to move back and forth between these is going to be very important. Now, you don't really need 3. Why? 3 is a special case of 2, right? Because I guess it's not until a little bit later, but that's okay. It's a special case of 2 because if you have a to the power of m minus n, what is that? You can rewrite that as m plus negative n, right? And a to the power of negative n bumps it down into the denominator. So it's leveraging this one over here, which honestly probably should have been 1.5 because we use it a lot. So you don't have to do this, but I would have, for future use, I'd probably make it here at 1.5 between 1 and 2. Because then we can boil down 3 and we can say, well, actually, you don't need 3 explicitly, right? You can just recognize that a negative power of n bumps it down into the denominator. Okay? And if you want to move it upstairs, right? If you have an exponent in the downstairs, let's call it, downstairs is the denominator, and you want to move it upstairs, how do you do that? By negating the exponent, right? So you can move between the two and it'll help you simplify things, right? Usually. So a to the power of m over a to the power of n. Now, again, you have to have the same base, right? That's going to be the key here. And it turns, so division turns into subtraction in the exponent. Okay. Multiplication stays multiplication. It doesn't care about the brackets. Okay, so if you can rewrite something as a to the power of m times n, then you can rewrite it as a to the power of m to the power of n, which is kind of handy sometimes. Okay. We've talked about things like quadratics, polynomials, and we know that you're not allowed to distribute a power unless you're multiplying or dividing inside, right? So now we have two different bases, A and B, right? And if you're multiplying inside, then you're allowed to distribute the m inside, and it goes on both the bases, right? So a to the power of m and b to the power of m. Okay. And so here, this is only if multiplying or dividing inside. The division is over here. Okay. So then you're allowed to distribute, but never if you're adding or subtracting inside here. Right. Same thing, if I have a over b to the power of m, then I can distribute that power inside, or usually what happens, I'm finding this little comma strangely distracting. I'm gonna, there.
Those other ones too, is it part of the thing?
It's just this and this and this. But that one I found especially distracting. Sorry. But now it's gone. I used whiteout, I guess, in a way. One of the ways, or most commonly what we do is not really distribute into the brackets. What we do is we rewrite a and b to the same power, and then I can extract it to the outside, right? So usually that's the direction that we move in, right? From here to here. Anything to the power of 0 is 1. Also a pretty basic, maybe that should be like 0.5, right? Start there. The ordering's weird. If I ever type these up myself, which I think I should, I'll change the order a little bit. Right, because this one's pretty key. Anything to the power of 0 is 1, which we saw when we worked with polynomials. Okay. Doesn't hurt to say it again, right? A to the negative n is 1 over a to the n, right? Or if you want to bump a to the n up top, upstairs to the numerator, you can rewrite it as a negative power. Okay. We've used this trick, right? Usually we're moving from the right-hand side to the left-hand side where I have to take the nth root of a. And how do I do that on my calculator? Because most calculators, mine doesn't have a fancy root button where you can specify the root, but the new one might. It does? Yeah. Fancy. So you don't need this one, but it's good to know in general, right? If I want to take the nth root of something, then if you don't have a fancy root button, what you would have to do is you would have to take a to the power of 1 over n, right? So if you want to take the 16th root of 4, then you would take 4 to the power of 1 over 16. Right? Similarly, if you have the nth root of a to the power of m, you can rewrite that as a to the power of m over n. Why? this comes from, so if I have the nth root of a to the power of m, I can rewrite that as a to the power of m to the power of 1 over n. That's allowed, right? From 9. Then, and maybe I'll write that here, from 9. But then if I have a to the power of m times 1 over n, I can rewrite that as a to the power of, or no, it's this one, sorry, 4. A to the power of m times 1 over n becomes a to the m over n, right? M times 1 over n. So this becomes a to the m over n from 4. So, good. No.
I don't get where the 9 or 4 came from.
Oh, here, from 9 and 4.
Oh, question 9. Okay.
Yeah. So it's like a mashup of the previous rules. Okay. Memorize me, please. Or something. Or at least have them close by so you can refer to them just to make sure. But we are going to use them a little bit today, so buckle up. All right. Do I have any examples that we could do? Let me just see if I can find some. Didn't pull any. Here's where I stole it from. Why not? So if we want to simplify a to the power of 4 times a to the power of 8 over a to the power of 7, there are a few ways that you can do this, but you're going to end up in the same spot. And so what I like to do is, if I have to simplify these things, the first thing I'm going to check is, do they all have the same base? And they do, right? They all have a base of a, so that's good. So I'll be able to zip these up. Okay. And so this, I like to bring everything upstairs, right? So that they're all being multiplied together. So my first step is to bring a to the power of 7 into the numerator. Now, what's another thing that you could do if you prefer, right? You could zip these up. A to the power of 4 times a to the power of 8 by 2 is a to the power of 4 plus 8, right? So you could zip those up first and then bring the a to the power of 7 upstairs. Either way. So there are lots of ways that you could do it. There are lots of ways to solve it. Here's just one, okay? And I encourage you to think about what your brain does naturally, right? And then just go with that, because here it doesn't matter. But for me, I like to bring that a to the 7 from the numerator. I like to bring it up to, from the denominator up to the numerator. And just for reference, what I'm using is I'm using 8, right? I'm rewriting a to the 1 over a to the power of 7 as a to the negative 7. So from 8.
Is it not? Three also? Like,
Probably. Oh, yep. Uh-huh.
Okay.
It is. So they're a little bit incestuous around here in the sense that, well, what are you using here? A to the power of m over a to the power of n. You're rewriting a to the power of n as a to the negative n from here. And then you're multiplying, but when you're adding a negative number, it becomes subtraction. So you can do without a lot of these, or not a lot of these, but you could do without this rule because it's just a special case, right? So, or 3, let's do that. Nice. What it doesn't say here is that this applies to any number of a to the powers of whatever. As long as you have the same base and you're multiplying, then you're allowed to add the exponents. Okay. So this becomes a to the power of 4 plus 8 plus negative 7, just to emphasize that we're adding, but it's a negative number. And so it's still true. It's going to be subtraction. And this is from 2. What do we get? 4 plus 8. Pretty sure that's 12 minus 7, 5. Is that true? 8 to the power of 5. So that's better than this. So we did it. We simplified it. Let's see if I can find, come on. We don't need to know that. Why not? If we want to simplify x plus 3 to the power of 5 to the power of 3 over 2. Ugh. Okay. Use x plus 3 as your base. Okay. So you just put blinders on, and x plus 3 is one thing. Okay. So you don't want to do anything like distributing the 5 because you're not multiplying or dividing in there. So what can we do? I'd say my go-to move would probably be to multiply these two powers. I'm allowed to do that from 4. Right. So here I get x plus 3 to the power of 5 times 3 over 2 from 4, which is going to simplify to x plus 3 to the power of 15 over 2. 5 times 3 over 2. You could leave it like this, but you could take the square root. Nice. That might look a little bit better, I think. What do you have to do to take the square root? Technically, now you don't have to show it, but technically what you're doing is you're splitting up that 15 and the 1/2, right? And so technically, right, you can rewrite this as, so 15 over 2 is 15 times 1 over 2, right? And so now you can as a mid step here, you could rewrite it as x plus 3 to the power of 15 times 1 over 2. Usually we skip that step, right? Because at that point, you're pretty comfortable moving around with exponents. And so here as a kind of a middle step, x plus 3 to the power of 15 times 1 over 2, right? Just rewriting it. Which means, and that from here, right, I can go straight to 10, but technically what we're doing, right, is we're splitting up a to the power of 15, or I guess from here, a to the power of 15 times 1/2, right, the brackets, and then the square root of a to the power of 15. Where a is x plus 3. So this is the square root of x plus 3 to the power of 15. It's really important that you keep those brackets because remember, x plus 3 is just one thing and we don't want to break that up. And this is from 10, I guess.
So if it was a number other than 2, then you would put that.
Then you put it in the crook here.
Yeah, and you just did the square.
Yeah, the square root is our go-to root, and so we don't usually write it. It's not wrong to write it, but I'm just lazy.
No, I got you. But if
Yeah.
it was like a 3 or whatever.
Yeah, then you have to specify. Yeah. Yes. Good. Okay. So should I try to find another example? Let's see. They're all kind of the same after a while. I don't really want to do these. And these are too easy. I think we've got it. Okay. Should we do this one? I know you probably didn't even get a chance to see. Here, if we want to simplify a to the 3 plus a to the 5 over a to the power of 4. One of the problems here is that I'm adding in the numerator, which means I can't zip these up because they need to be multiplying. And so I have to keep them as if they're adding. Okay. But I'm dividing by a, so there are lots of ways that you could do this, right? What's one of the ways? Probably the easiest way would be to extract a common a here and then divide by a, right? Because you're only allowed to cancel this a if you have an a in both terms, right? And so if we want to simplify this, right here, this is the problem here. We can't simplify addition. So we have a to the 3 plus a to the 5 over a, and then all that's to the power of 4. Again, lots of ways that you could do this. What's another way? If you didn't want to extract an a, you could use a to the 3 plus a to the 5 as one thing, right? And then multiply it by a to the -1. Kind of makes more of a mess in my opinion, so I'm not going to do that. But that's another way that you could do it and just kind of grind through it. Okay, as long as you follow the rules of the game, then it's all fair. So what I'm going to do is I'm going to pull out a common a, which means that I have a times a to the power of 2. What am I technically doing there? Okay, let's take it one step further, because technically what I'm doing, or what you are doing, is you're rewriting a to the power of 3 as what? A to the power of 2 plus 1. Right? When you're pulling out an a to the power of 1. Technically what you're doing is you're rewriting a to the power of 3 as a to the power of 2 plus 1 plus a to the power of 4 plus 1. Taking it way back. Just to show you what you're doing technically. So here, this is from 2, I think. Yeah. Which means that you can rewrite this as a to the power of 2 times a to the power of 1 plus a to the power of 4 times a to the power of 1. And I'll emphasize that a is to the power of 1 down in the denominator for a little bit. This is still from 2, it's just the opposite way. Right. So this is what allows you to pull out that common a to the power of 1, but also now you can see that you have an a to the power of 1 in each of the terms, right? And so now you could pull it out here or just cancel right away. That's up to you. What would you like to do? Cancel right away? Pull it out maybe. Will be proper. A to the power of 1 times a to the power of 2 plus a to the power of 4 over a to the power of 1. That's just from a common multiple rule. But now I'm allowed to cancel, or canceling, I'm having to dig down into my exponent rules. How am I canceling technically? This becomes a to the power of 1 times a to the power of 2 plus a to the power of 4 times a to the negative 1 to the power, and maybe I don't need these huge brackets anymore. And that's from, I want to say 9 or 8 or something. From 8. I can bring that a to the negative 1 into the numerator. What if I ignore this little guy? I can just keep him outside. I can move a to the 1 times a to the negative 1 together, and I can just work on those two. They're being multiplied. They're multiplying this, but it's not the same base. And so, we'll just keep it separate for a little bit. And I'll keep a to the power of 2 plus a to the power of 4. And then I'll bump the a to the power of 1 times a to the negative 1 to the power of 4. And I'll throw some brackets around here just to emphasize that now I'm multiplying the same base, which means that I can zip this up as 1 power. And that's from 2 or 3 if you wanted to go there. I think it's 2. So now you can rewrite that as a to the power of 2 plus a to the power of 4 times a to the 1 plus negative 1 to the power of 4. Still from 2. And that's technically how you're canceling and why they cancel, right? Because yes, but this is an exercise in exponents and how they behave and technically what you're doing. Yes, you could have canceled. You could have canceled immediately. You could have said, I've got an A here, I've got an A here, I can pull them out. A, cancel, done. But like I said, this is an exercise in, for me, in working with exponents, right? Technically what you're doing here, I never take it this far.
No, you can go this far.
Fun, right? So now you have a to the power of 2 plus a to the power of 4 times a to the power of 0, which is 1 by some rule. That should have been rule 0 by 7. And this is equal to 1 from 7. So now I have a squared plus a to the 4 times 1, which I don't need to write anymore because I got sloppy and wrote it here. Fine. Now it's gone, it's canceled, but I still have a to the power of 2 plus a to the power of 4 to the power of 4. Now there's nothing I can do here. That's simplified because I'm adding inside, right? Technically what you could do is you could expand it, right? And so we can't simplify further. Since a to the power of 2 plus a to the power of 4, I'll just highlight the reason is the addition inside. To the power of 4 is a to the power of 2 plus a to the power of 4 times a to the power of 2 plus a to the power of 4. Let me just copy and paste that. Should have written it nicer. Need one more. You could expand that, but I would argue that that's not simplified. It's longer and bigger and grosser, and no thank you. Okay, but that's my warning is when you're adding inside or subtracting, right? Then you can't distribute this power inside. You can only do that if you're multiplying or dividing, because then you'd have to accordion it out like this. But this is from a rule. This is from rule 1, right? And so this is from 1. I can rewrite it like that. Treating a to the power of 2 plus a to the power of 4 as the base, right? Just ignoring that it's kind of bigger than what we're used to. Something to the power of 4 is that times that times that times that, right?
So you can't go like a 2 plus 4 would be a to the 6 and a 4 plus 4 is 4 would be a to the 8 because it doesn't add up. Is it that way?
Do you mean like multiply this inside here?
Well, like what I would do is have like add them individually to be like a to the 6 plus a to the 8, but it doesn't add up when you look at your expanded form.
Yeah.
That's why.
That's why. Because there is no exponent rule for addition or subtraction. So you have to do it the old-fashioned way. You could FOIL this, but it would take half a day, right? You could go a to the power of 2 times a to the power of 2 plus a to the power of 2 times a to the power of 4. Do them step by step, build out incrementally, but don't do that because this looks nicer to me, right? Good. Okay. So those are exponent laws and they've been lurking everywhere. And I can't believe I haven't talked about it before, but now we have. Okay. Let's see here. Let's go back to our chapter 4. We did the first example and then we made up some other examples last day because I didn't have these examples posted yet. And so here, I'll say back to exponential, even though those are exponential functions, but they're exponent laws. Back to exponential functions. What if we have to interpret this equation? So P of t is usually used to denote a population at time t, right? Usually. And so I'll say P of t is likely a population size at time t. That's my guess. We know that whatever value is up front, so our a, remember from our generic f of x is a times b to the power of x. A is the starting value, which means that p of 0 is 1,000, right? That's the initial value. Nice. So here, what's one of the clues that you're using? This you can rewrite as 1 plus r, right? 1 plus r, but it's less than 1, so that tells me that r must be negative, right? So 1 plus r is equal to 0.83, which means that r must be negative, what'd you say, 0.17? Which means the population, since r is negative 0.17, the population is decreasing at a rate of 17% per year. I'll just throw in, we always have to state our assumptions. What are some of the things I'm assuming? I'm assuming P stands for population size. That's not necessarily true. I'm assuming time is in years. Could be minutes, could be whatever, but just for interpretation, assuming time T is in years. Identifying things that you're assuming is just a really good general skill to have, right? Not just in math, but in any course that you're taking. Because sometimes you do have to assume stuff, but you also have to declare it, right? But especially in math, you have to declare things that you're assuming. Okay, and stats. Probably chemistry, physics, whatever. Yeah. For sure. Yeah, and it's one of those skills that, you know, you're learning in school. Can't really test it though. Just one of those things. Okay, so good. So I'd say that's my interpretation, right? The population is decreasing at a rate of 17% per year from, I guess I'll add from an initial population size of 1,000 units. Right. Not committing to anything. Good. How about another example? If we have to find an equation for an exponential passing through 0.03 and 318, what can we do? One of the first things that we have to tackle in our exponential function, right? And so step number one is usually step one, is find the initial value. F of x is a times b to the power of x. So you're going to find a. In this case, we're starting off nice and slow. Why? We know that a is when x is 0, right? That's your initial value. So f of 0 is equal to a, which means that, 0a has to be a point, but we know we're given 0, 3. So that's nice. So a must be 3. Since 0, 3 is given. Oops. Okay, that's good. So then we have f of x is equal to 3 times some b to the power of x. Where do I go from here? Well, first I should probably make sure this looks like a b and not a 6. I don't think I changed it much. There, that's beautiful. 3b to the power of x. We use the same trick, right, that we did way back when we had linear functions, right? We wanted to find equations of a linear function that were, for example, perpendicular to some line, right? We knew how to manipulate the slopes, and then we had to do what? We had to take that coordinate, right, and use the x and the f of x to solve for the missing part. So here, this is an x, f of x point. So if x is 3, f of x is 18. So we're given that f of 3 is 3 times b to the power of 3, and f of 3 is 18. So this is what we're given. Because what do we want to do? We want to try to find b, right? Using that point. I know it has to pass through that point. And so now I can figure out what b is. So going nice and slow, right? 18, you have to divide by 3 first, right? Move this 3 over to the left-hand side. So you get 18 divided by 3 is b to the power of 3. 18 divided by 3, is that something nice or bad? Something nice. Naughty or nice? That's great. B to the power of 3 by our exponent rules or your snazzy calculator, because you have any root function. But what are you technically going to have to do to solve for b here? You're going to have to take the third root of 6. right? And so this means that b is equal to 6 to the 1 over 3 from, I can't remember which rule, 9. And, oh, I did something weird. 6 to the power of 1 over 3, because I do not have a snazzy button. I get b is roughly 1.817120593. Roughly. Nice. So now I have my base. We're not asked to interpret this, right? But this is my 1 plus r, right? Which means that my rate, it's increasing at 81.7% per t, right? Whatever t is. So here, this is my 1 plus r, which means that r must be 0.817-ish. Okay, I'll do my squiggly equals. There. Which means it's growth. Growth because it's positive. Good. All right. Nice. Let's see what the next example is. Step it up a notch. What if we have to find an equation for an exponential passing through the points 2, 5, and 4, 1? Uh-oh, no initial value. Okay, that's okay. Let's just take it nice and slow and see what happens. We're given that if x is 2, f of 2 is equal to 5. That's what that says. All right. And we're given that if x is 4, f of 4 is equal to 1. That's all we have. And we're told that it's an exponential function. So we know the bare bones of the exponential function are f of x is a times b to the power of x. I don't know a and I don't know b, but I do have 2 points, right? I have 2, 5, and 4, 1. So what I'm going to do is I'm just going to put those in individually and see what happens, right? See what I can find. So this is what I meant by you have the tools from a different section, right, in how to solve these, but we're just seeing it for exponential functions instead. So maybe I'll use different colors here. Make this one green. It changed everything. Oh boy. No. I'll just write it out again. Only because I want them to line up when I write them out. Okay, so let's focus on 2, 5. So when x is 2, f of 2 is 5. So we have f of 2 is a to the power of b to the power of 2. F of 2 is 5, a to the power of b to the power of 2. Okay. Not much else I can do there, but let's just parking lot it for a little bit and let's chip away at this little guy, right? 4, 1. So if I have f of 4 is a b to the power of, oops, 4, that'd be confusing. f of 4 is 1. A and B have to be the same here, right? This A has to be the same as this A, and this B has to be the same as this B, right? Otherwise, they're not the same function. Okay? And so here, let's just make a note here. These A and B must be the same. So what could I do? I could set them equal to each other, but they're not equal, right? This one's equal to 5 and this one's equal to 1. But what's something I could do? I could move this 5 and the 1 over to the right-hand side and force them both to be 0. And then I can use 0 as my gateway drug. Right? And so here, set both equal to 0, which means that 0 is, oh, and maybe, just to emphasize it, I'm going to have a to the power of b to the power of 2 minus 5 is equal to 0. And then on this side, I'm going to have a to the power of 0 is a to the power of b to the power of 4 minus 1. The only reason I wrote them back to back like that is that I can just smush these together, right? 0 is equal to 0. So this is my, oops, it's not even approximate, it's exact. 0 is equal to 0. So now, if I've got the same thing in the middle, I don't have to write it out anymore, right? Then, right, if A is equal to B and B is equal to C, then A must be equal to C, right? And so I have AB squared minus 5 is equal to AB to the 4 minus 1. Okay. So now, okay. What's another thing we could do? I could bring the 5 over here, just because I don't like negatives, right? They're going to haunt us, but still, AB squared can be AB to the power of 4 minus 1 plus 5, right? Or what's another thing I could do? I could bring the A's over to one side and the numbers over to the other side. Maybe that's cleaner, right? And so if I have AB squared minus AB to the 4 is negative 1 plus 5, right? Just to illustrate here, I'm doing a little switcheroo in one go. Now I have, how do I want to do this? I'd probably pull out a common A. So I could have A times B squared minus B to the power of 4 is 4. So now I could rewrite this as A is 4 divided by B squared minus B to the 4. A is 4 divided by B to the power of 2 minus B to the power of 4. Okay. Then what? Now I have this A, good. And it doesn't matter which one you use here, right? But what you're going to do is you're going to plug in A is equal to 4 over B squared minus B to the 4. And then your only variable here is b, which you'll be able to solve for. Let's do, doesn't matter. Let's use this one, the first one. Substitute a equal to 4 divided by b squared minus b to the 4 into f of, actually, 5 is equal to ab squared. Which means that 5 must be equal to 4 over b squared, oops, b squared minus b to the 4 times b squared. Okay. You can see why we needed to work on our exponent rules, right? We're going to pull out a common b squared from the denominator and cancel immediately, but remember that you're technically making the power negative and then adding the like term, or adding the same base. 5 is, but you guys didn't like that very much. B squared times 1 minus b to the power of 2 times b squared. Right. Technically rewriting b squared as b squared times 1, or b to the power of 0 if you want, and minus b to the power of 4, which is b to the power of 2 times 2, which lets you extract this. But we already did that, all that work once. Now, because these are multiplying, right, I can cancel that b squared. Okay, let's just write this out again so it looks a little bit nicer. 4 divided by 1 plus, or 1 plus, that'll make a mess, minus b squared. Solving for b, you're going to multiply 1 minus b squared over to the left-hand side, so you get 5 times 1 minus b squared is 4. Now this 5 you're allowed to distribute because we're trying to shake out the b. So 5 minus 5b squared is 4. So I get 4 minus 5 is negative 5b squared is negative 1. So b squared is negative 1 divided by negative 5. So 1 over 5, because those are going to cancel. So then b is plus minus the square root of 1 over 5. Plus minus because when we square something, even if it's negative, it becomes positive, right? So we have to attach that plus minus. Usually we ignore the negative, right? And so let's think about what b is. B is this base of the exponent, and we already forced b to be positive. And so here, but we force b to be positive, which means that b is the square root of 1 over 5, or 1 over 5 to the power of 1 over 2. Now, I don't think this is going to be anything nice, but let's just try it. It's not. But I think we're okay with using an approximation. The exact value would be the square root of 1 over 5, but let's just use approximately 0.4472. Close enough. Oh, A is 4 divided by b squared minus b to the 4. Hey, maybe we should keep the square roots, get the exact values. That might be nice. So now, recall, A was 4 over b squared plus minus b to the 4. And to keep it on the same, or try to keep it on the same page, I'm gonna have 4 over the root of 1 over 5 squared, which is just gonna be 1 over 5, minus the root of 1 over 5 to the 4th. Guess I'm not gonna be able to keep it on the same page, but that's okay. Right. The root squared is going to cancel out. Why? Because I can rewrite this as 1 over 5 to the power of 1 over 2. 1 over 2 times 2 is 1, and that's why it's just 1 over 5. Exponent laws, they're everywhere. So here, if I have 4 divided by 1 over 5 to the 1 over 2 times 2, I'm going to write it this way to emphasize that they're at play here, the exponents. 1 over 5 to the 1 over 2 times 4. 4 over 1 over 5 minus 1 over 5 squared. Right, 4 divided by 2 is 2. Okay. Really making us work for it today. Good thing we introduced those exponent rules, huh? What can you do? By one of the rules, you can distribute this square inside, right? 1 squared over 5 squared. Let's do that. So I have 1 over 5 minus 1 squared over 5 squared. Now I don't have a common denominator anymore, so I need to force that common denominator because I need to add and subtract this, these fractions. And so I'm going to force it by multiplying by a convenient value of 1 times 5 over 5, right? Because I want 25 in the denominator. And so now I get 4 divided by 5 over 25 minus 1 over 25. I need this common denominator in order to subtract these. And we're so close. 4 divided by 4 over 25. But this is a fraction over a fraction, right? 4 is really 4 over 1. And so I get 4 over 1. And I like to write the over 1 just to emphasize that it is just a fraction. And you can write any number as a fraction. And then 4, oops, thought I was in pointer mode. 4 over 25, you have to flip and multiply. And so you get times 25 over 4. And 4 over 4 is going to cancel. And what do you know? A is 25. And A is your starting value, right? And so your initial, whatever, population size or amount or whatever is 25. And so f of x is a to the power of b, or times b to the power of x. So f of x is 25 times, and should I use the root of beta, the root of 1 over 5 maybe, just to be proper? I'd be fine with if you wanted to use the approximation, but let's just use the root of 1 over 5. We worked hard to get it, so if you got it, flaunt it, right? Clean this up. 1 over 5. Ta-da! You did it. There's your function. That's a lot of work and a lot of exponents at play. And toss in some fractions. Uh-oh, boy. Makes for a really good test question though, right? I feel like this could be half a test too. Find an equation for an exponent passing through these 2 points. And with my last 2 minutes, we're going to graph this in Desmos just to make sure. Maybe. 25 times the root of 1/5. Step it out, close the bracket, to the power of x. Oops. To the power. Okay, fine. It's doing it. And we had, when x was equal to, was it 2? What were the points? 2, 5, and 4, 1. So what I like to do is I just like to put x equals 2 on there and just make sure it intersects at 5 and x is equal to 4 and make sure it intersects at 1. We did it. We did it. We did it. They said it couldn't be done. Hey, I'll try to take a screenshot with the points included or not. Good job. So
You basically set them both to 0 and you mess around with it until you get on either side the A's and B's
yep.
until you're down to 1A or 1B.
Mm-hmm. And then you substitute that back in.
Back into either one.
Yeah, doesn't matter which one. And then you're in. Right? This was at 2, 5, and this was at 4, 1. Whee! And with that, I release you.